Okay, welcome everyone. We're going to go ahead and get started. I want to welcome you all to East Valley Astronomy Club. My name's Andrea Matthias. Our beloved president couldn't be here with us tonight. He's on an astronomy cruise right now. So I am going to lead our meeting tonight. And just like Steve does every month, I want to welcome you, and I want to welcome the folks that are on Zoom. And as always, we hope that you enjoy yourselves. We hope you learn something interesting. We hope you make a new friend, and we hope you reconnect with old friends. All right, so let's make sure our cell phones are all turned off. And while you are doing that, I want to remind you that during our presentations today, you'll have an opportunity to ask questions. And if you have a question, you'll raise your hand, and either James or I will bring the mic to you. These mics are really magical. As you are talking in the mic, if you hold it too far away, you'll find that you can't hear what the person is saying. So get that mic right up to your mouth, please. Thank you. All right. Okay, so with that, do we have any visitors tonight that would like to raise their hands and share a little bit about themselves? You can tell us your name and how you discovered EVAC, what your astronomy experience is, or maybe you're just getting started. Do you have a favorite thing about or in space? Great.
My name is Samudra. I found you guys, I don't know, I think mostly just searching like stuff to like experience astronomy. I'm a beginner when it comes to astronomy. I've just bought a telescope, and I'd say my favorite thing about space is probably like high energy physics, or like black holes, pulsars, that sort of stuff.
Thank you. Anybody else want to introduce yourselves? Okay. Oh, did you want to also? Sorry, I'll be right with you.
I'm Samudra's father. My name is Pradyumna Gupta, and his interest in astronomy is also, making me interested. I mean, this is probably some hidden desire I had, and so let's see how it goes.
Thank you. Okay, we have another one back here.
Hi, I'm Andy. I'm actually from the Chicago area. We're on vacation, so I had to get out of the rental house and do something. But actually, I followed the club on a Facebook group site, because whenever I come out, I always bring a telescope. Sometimes I actually make it out somewhere. A lot of times I'm just in wherever I am looking at what I can see. But I can tell you, I do see a lot more stars here than when I do by my house, even though I'm outside of the Chicago area. We still get a lot of light pollution.
Anybody else? Okay.
Yeah, my name is John, and I just wanted to, I don't know how many others, I see some other gray hair here, but in 1957, I was outside our house in Minneapolis, and Sputnik went overhead and kind of hooked me right there. So I've been doing astronomy stuff up and down since then, just getting back into it.
Welcome. Any other guests that would like to introduce yourselves? Okay, very good. Well, welcome. We're happy that you're here with us tonight. Okay, so our meeting we have a few announcements to share at the beginning, and then Alice will get up here and share what's going on with outreach. We'll have James speak about how to pick the right astronomical targets that will match your sky and your telescope. And then we have Mark Johnston here to talk to us tonight about the sun. All right, so Steve reached out. He found a really cool website. It's called gravityfinder.com, and it's really fun. You can click on it. I want to see if it'll work here. You know what? I might have to do it over here. And it will show you how much you would weigh on another planet. But it shows you more than that. I don't know how to switch it out. Oh, right. Thank you. There we go. So you can click explore up here and it's super fun. Is it loading? All right, so down here, I need to move over here so I can see. All right, so you can pick a world, you can pick an exoplanet, you can pick a planet that's in our solar system and type in your height, your weight. I'm not going to share my height and weight with you, but it's really quite fun. You can also look at galaxies, black holes, stars, super fun. So I encourage you to look at that. It'll be on the EVAC website if it is not already. But that, do I just drag it right off, John? Okay. Very good. All right. So that is gravityfinder.com. Okay, the Grand Canyon Railway has a special opportunity for volunteers. They have their Star Train, and they are looking for volunteers who are available in early October, and it does coincide with our All AZ Star Party, but that's okay. But they are looking for about 10 to 15 telescopes or volunteers who are willing to go on up there to a remote site. And then the Star Train will bring guests to you, and you will spend about 90 minutes sharing the night sky with the guests in a remote area south of Tucson. And you will also get to enjoy free camping for the evening. So if you are interested in that, you can email Steve Rodas of Swaro Astronomy Club or Ranger Lane Raider. And this is Raider_Lane at nps.gov. But if that's something you'd be interested in, go ahead and email those folks and they can give you more details on that. All right, next week we have a partial lunar eclipse. If you'd like to learn more about that, you can go to inthesky.org. I went ahead and looked up the real time. Military time can be a struggle for some folks, but next Thursday, it'll begin at about 6:25 p.m. We'll have a partial lunar eclipse. All right, and now it's time for Alice, our sweet Alice.
Thank you, Andrea. Sweet and a little salty. All right. So one of our ways, actually we have two ways. Let me see, let's go over here. All right. So a lot of times I get asked, why should I become a member of EVAC? And there are many reasons, but for me, it would be you're able to volunteer for outreach, and you're also able to volunteer for GRECO, which is the Gilbert Rotary Centennial Observatory, which is just down the sidewalk over here. It is open every Friday, Saturday night, sundown until 9:30. You can volunteer there. You can be an operator. You can work the door. If it's something that you're interested in, you can talk to the manager, which is Claude. At the very bottom of the screen down there, you'll see the email. It says greco@evaconline.org. Reach out to Claude. Let him know you'd be interested. You can pick and choose what days. And yeah, there we go. So there's the first one at GRECO. The next one is my responsibility, which is our public outreach. So what does that entail? So basically, we do outreach for public events like schools or libraries, HOAs, that sort of thing. And I have, actually, it's starting to be 3 types of volunteers, but the first type of volunteer I need is telescopes or binoculars. And you would bring your equipment to the party and have an object that you're interested in viewing that evening and share that object with the guests that come up to you. The next would be what we call walker helper. And this person checks in on all of the astronomers with telescopes, make sure they don't need a bathroom break or they might need a water. Also helps to keep our guests, remind them of telescope etiquette, like no running around the telescopes, no food or drink, that kind of thing. And we also have this beautiful astronomy booth that I'm starting to book for our star party season, which is going to be ramping up here in October. A lot of my repeat schools have found out that we have an astronomy booth, and they want an astronomy booth along with the telescopes. So I will need volunteers to help work the astronomy booth. Don't feel intimidated. It's super easy stuff. Our astronomy booth is pretty basic. 3 types of telescope, little models. We have Earth model, a sun model. We have planisphere. We have a beautiful Ori. So it's really easy. Don't be intimidated that, oh, I can't do that. So there's the 3 ways you can volunteer. You plan on just whatever fits into your schedule is you choose those star parties. I do have them posted on the EVAC website under events and meetings. However, if you do want to volunteer, you should really sign up. You absolutely need to sign up for the free list EVAC outreach at the very bottom. Sign up for that mailing list. I send out reminders, cancellations, updates. Everything is communicated through that website. So you really need to be signed up for that to stay informed. All right. So our outreach season right now in the summer is pretty slow. We have a star party the second Friday of every month except December with Greco over here complementing it. And so this month, all of our volunteers, actually that was last month, that was July. Wow, okay, well that was July. Oh, Desert Botanical Garden. This one was not part of outreach, but this was one of those that the Botanical Garden reached out to us to see if any volunteers would be interested in participating in a, I think it was like a flashlight night kind of thing. Yeah, and so here are our volunteers who went to that. The only issue that Deb actually said, he said that it was cloudy. So they were looking in between clouds, but hey, they made it work. Okay, here is this month's star party right here. So everybody right there, it was, they were feeling adventurous. So we were predicted to have a hole in the clouds. Didn't quite know if that was going to happen. You know, the weather forecast is 50-50, but I always say, let's go. If there's no rain predicted, let's just see what happens. And so, yeah, we had a great turnout to see, maybe we'll view something, maybe we won't, but we had about an hour and we were able to view about half a dozen objects in that hour time, which worked out really good. One of those objects was Venus. And Gordon has this pretty cool Venus display that he put up so guests could go view Venus, what phase it was in, and it was in kind of a quarter phase or half phase. And then they could come over and see, hey, what phase is it? And they could pick it out and they could see how that happened. It was it's actually a pretty good hit having that with our telescopes. So great, great time. Thank you to all of you who volunteered for that night of maybe, maybe not. And a huge thank you to all of our volunteers who volunteer for outreach. I believe the most important thing that you can ever do is volunteer your time, since that is so valuable nowadays. And I appreciate it. And most importantly, our guests at these parties appreciate it. So thank you so much. So upcoming Outreach Star Parties events, Andrea just mentioned next week on Thursday is the partial lunar eclipse. We will be having a star party out on the lawn by the observatory, and we'll be viewing the partial lunar eclipse from about 7:30 until 9:30. I invite all of you as guests. If you don't want to volunteer a telescope or volunteer for outreach, please come out as a guest and enjoy the view, socialize with some of the members, kind of see what a star party is like. Our next one is going to be in September, again, second Friday star party. And then the Apache Junction Multi-Generational Center every year holds a Mad Science event. It is a pretty big deal. It's pretty awesome, actually, very busy. And they've requested our astronomy booth. as well as telescope viewing. So if that's something you're interested in, sign up. Details will be on our website under events and meetings. But again, sign up for that free list because next week I'll be sending out more detailed description of these next two, the September 11th and September 19th. Oh, excuse me, Star Party. If you have any questions about outreach, feel free to come and see me during the break or after the meeting. I'm happy to answer them. All right, thanks, Andrea.
Thank you, Alice. All right, it's time for our member presentation for the evening. So James Yoder is going to come on up and share with us observation optimization.
Before we get started on that, just a reminder to you guys, if you are interested in star parties, the Hyman Rim Ranch Star Party, Hyman Rim Ranch Star Party is next month. If you're interested in signing up for it, I think it's, I don't have the dates with me. I think it's 11th through 13th. But it's at a nice, really dark site, and it's only $10 per person if you're a member, and you get breakfast and dinner free. So if you're interested, I've got cards. You can come talk to me and I can show you where you can find out more information on it. It should be fun. Next scene, let's talk about, oh, also, I might next month announce the class, beginners class. If anyone's interested in finding out more details about it, it usually runs about 4 or 5 labs and 4 or 5 classes, Zoom meetings and labs. If you're interested, come up and talk to me, and I've got card. I'll give you my card, and we'll put you on a distribution list, and then I'll try to figure out a schedule for the class if enough people are interested. All right. So presentation. So there's 2 things that I wanted to accomplish with this presentation. One is if you own a telescope and you have an observation site, what's appropriate targets for you to try to look at. The other thing is if you're considering buying a telescope and you know what kind of objects you want to look at, this might help you decide what type of telescope you want to think about purchasing that would be appropriate for the targets you're interested in. Okay, so what we're going to do is classify the different things that you can look at in the sky into 3 types of things. Solar system type of objects. These are bright but have a surface area to them. Point sources. These are more like stars, open clusters, things that are individual little points that you can't measure a size on. And then extended objects. These are galaxies that actually have a surface area to them. Nebula is another example of that type of things. So we're talking about 3 different classes of objects. This is what I was talking about before. If you already have equipment, hopefully you're going to learn out of this what's appropriate targets for your equipment that you have. And if you're shopping for equipment, this may give you an idea what kind of equipment you want to purchase. So we already mentioned the 3 different types. Again, the extremely bright. These are solar system objects, really bright, so you don't have to worry about gathering light so much. Point sources, let's see. Carbon stars is another example. Double stars would be another example of point sources. And small planetary nebula possibly too. Extended objects, again, we're talking about galaxies, maybe globular clusters, and large nebula. Okay, so as I mentioned before, so here's again the 3 classes with examples. When we're talking about solar system, we're talking about the sun, the moon, planets. Point sources, here's some examples. Double star systems, butterfly cluster, ghost of Jupiter, and so forth. Extended objects, Whirlpool galaxy, Messier 10, and so forth, the Pipe Nebula and such. Before we got started talking about the equipment, we also got to understand some of the basic terminology used in astronomy, and one of them is called Bortle scale. What Bortle scale is a measure of how bright the background sky is. So in a place like the city here, our Bortle scale, I think, is 4 in this metro area, which is very bright background. where if you go out to like picket posts where we go a lot of times, I'm sorry, picket post is a board of 4. We're more board of 7. So the lower the number, the darker the sky. So you want a nice dark sky. Why is that important? Because we're looking for contrast between the objects we're looking at and the background sky. We'll talk about that here in a little bit. To talk about the contrast, we got to talk about surface brightness. So what's surface brightness? Surface brightness applies to things that have a surface to them, like I was talking about galaxies, nebulas, such like that, actually have a area that you can see when you're looking at them through the telescope. And so the surface brightness is a measurement of all the light that's coming from an object, and that's divided by the area of that object. And from that, you get a measurement called the surface brightness, and it's in mags per arc second squared. The lower the numbers, the brighter the object is. And this is a very rough estimate. This assumes a lot of things. For instance, it's assuming that the object is uniform in brightness. And anyone that does astronomy knows that these galaxies or other things have brighter regions and darker regions. So that's not really a good assumption. But this number is a good first guess type of thing, a first approximation. So when we're talking about contrast, we want to know the contrast between the object we're looking at and the object or in the background sky. So that's the contrast. And be able to identify something, studies have shown you have to have at least a half a magnitude difference between the object you're looking at and the object in the background sky. Something I also forgot to mention that, when we talk about surface brightness, we're talking about it applies to galaxies and such. It does not apply to something like a star because that really has no surface area per se, multiple star systems. But you can use the magnitude as a proxy for the surface brightness because that's a measure of all of the brightness on that object. So, okay, so contrast is the difference between the object you're looking at and the background sky. So why does the sky matter? Here's some examples of what some galaxies may look like in a nice dark sky, suburban, and the city. You can see as the background is getting brighter, it's more difficult to see galaxies. And if it's a really dim galaxy, it can get to a point where the galaxy is dimmer than the background sky. At that point, it won't make any difference what equipment you have. You'll never see that galaxy. Okay, so now let's talk about telescopes. So the information we just talked about there is more about the site you're at. So the site is going to determine how bright the background sky is. The telescopes, the things that we need to worry about when we're trying to figure out what we're going to look at is the resolution of the telescope, and that's directly related to the size of the aperture of your telescope. And then the light gathering power of the telescope, which is also related to the size of the telescope. The bigger the mirror or the lens that you have, the more light you can gather in your telescope. As far as the resolution, the larger the telescope, the smaller resolution you can see. For instance, if you're looking at double stars, if one's really close to each other, you may need a larger telescope to resolve those stars. That's up to a point. At some point, the atmosphere becomes a limiting factor, not the size of your telescope. And that's generally, for a good telescope, it's about 9.25 inches. After that, getting a larger telescope may not make much of a difference between resolving stars and stuff like that because the atmosphere is more the interference than the size of your telescope. With light gathering power, that's not the case. The bigger the telescope, the more light you're gathering, no matter what the atmosphere is. So why are mounts important? Mounts generally aren't really considered so important for determining what to look at. But if you're in the city like here, and you generally have a mount that you have to star hop to, that means you look at this object. I know where this star is. I'm trying to get to this object over here, but I don't know how to get there directly. You go to familiar stars and you hop your way over to the stars that you're familiar with, and then you go to the object you're looking at. Well, if you're in a city like this, there's not many stars to hop with. So at some point in the city, for instance, you're going to have a go-to telescope, or else what's called a push-to telescope, which is like a smartphone attached to your telescope that tells you move your telescope this far, and then you should be there. So if you're in the city, you really have not much choice unless you're looking at really bright stuff, but to either have a go-to telescope or a push-to telescope. Darker skies, you can star hop, and you can actually see a lot of stuff with star hopping in a nice dark sky. So the amount is not as important if you're in a dark sky. So another aspect of telescopes is the focal ratio, and that's the size of the aperture to the focal length of the telescope. So the way I look at it is the F ratio kind of tells you what the natural magnification of that telescope is. So for instance, if you have a high F ratio telescope, it's going to see a lot more smaller area of the sky, which is more magnification, than a telescope with a low F ratio. And that's because when you're looking at the magnification for a telescope, it's a combination of the aperture size and the size of the focal length, the focal length of your telescope and the focal length of your eyepiece. So you can get the same magnifications with a higher focal length eyepiece on different telescopes. So you can still match the magnifications, but it's more difficult on a low F ratio telescope. These are some resources that you might want to consider when you're trying to figure out what objects to look at. These are all free. The Sky Maps website has a nice printout of the night sky for the month. And then these are also free online catalogs. The Star Hopper's Guide to the Universe is great if you're a star hopper. Shows a lot of different objects. And it's a PDF file you can print out. And then there's my constellation guide. If you want to just focus on a constellation and look at stuff in the constellation, this is a good theme for that. And then the new catalog of stellar rich fields, which is again one of our local astronomers here has made this, is great for if you have binoculars. So these are good free resources. Okay, so making the decisions. These are the guidelines. These are guidelines. There's always going to be exceptions. So for instance, when I say you can't really see nebula in the city, well, you can see M42 all the time, no matter what city you're in, because it's a really bright nebula. But for the most part, nebula is not going to be available in the city, and same with galaxies. We'll talk about that in a little bit here. So just keep in mind, there's always exceptions to what I'm talking about on this. And again, this is recommended stuff. You still may be able to use gear that I say isn't optimal for the conditions, but it just may not be quite as great as if you had the right telescope for the right objects. So again, I was trying to figure out if you already own a telescope and you've got your sight, this might help guide you to figure out what type of objects you want to focus on to have the most success. If you're looking for a telescope, figure out where you want to go observe and what kind of objects you're interested in, and then this will help guide you what kind of telescope would be appropriate. Okay, and this is really the whole point of this discussion was, first I've got the column over here with the sky conditions. So for a darker site, say if you're going out the picket posts out here, if you're looking for solar system, double, multiple star systems, small planetary, nebula, and so forth, a high F ratio telescope is probably ideal for you. That would be this Massatoff-Cassegrain, Schmidt-Cassegrain, and Dobsonians. Those are all pretty good telescopes that have naturally high magnification to them. If you're looking for galaxies, nebula, dark nebula, large planetary nebula, open globular clusters, and so forth, that's when light gathering is really key. So you want a large aperture telescope. Dobsonians are the best bang for the buck for large aperture. Schmidt-Cassegrains, you'll see Schmidt-Cassegrains in all these lists. They're kind of the, they're really good at everything, but they're not a master at anything. They're just really a good all-purpose telescope. So if you're just looking for something that's going to behave well in everything, Schmidt-Cassegrain's a really pretty good choice for that. If we're talking about dark nebula, large planetary nebula, and so forth, you want a low F ratio telescope. So these are open clusters, refractors, Dobsonians, binoculars. For city viewing, stuff like galaxies, nebula, globulars, those are pretty much out of the question. So don't bother with that stuff unless, like I said, there are some exceptions, but very few. I do a lot of city viewing myself. When I do city viewing, I'm focused on solar system stuff like the moon, the planets, multiple star systems. City viewing is great because it really doesn't make any difference. So, and I really think multiple star systems are undersold. There's some really pretty multiple star systems out there. You can look at small planetary nebula and some open clusters in the city. And those are high F ratio telescopes. Again, the Massatoffs, Schmidt-Cassegrains, Dobsonians, so forth. And I think that about covers it. Let me check. Okay. So this is where you can, if you're interested in finding those free resources I was talking about, go to my website, artcentrics.com. Come up and get my card also, or stop by and get my card. I have the website on here. Go to the book section. Whoops. And in the books, you'll find the links to the PDF books I was talking about. They're all free. You just print them. And I think they're pretty nice resources. If you haven't taken a look at it, you should check them out. And I guess we can take questions. Andrea's coming up.
You didn't really touch on seeing, but let me ask you a quick question. Is there any place around here that generally has better seeing? Because when I look at the apps, no matter when I look, it's always average.
Yeah, I'm a really bad person to ask about seeing because I don't pay, I figure I'm at the place that doesn't make any difference. But I understand like fields and over by water, type of things. So where it's cooler areas, it's supposed to be better for seeing. But that, I'm sorry, I don't really pay much attention to that. I guess Andrea's going to the next person.
One place I'd suggest, and only because somebody was there with their telescope and showed it off, is it's down Lost Dutchman State Park. There are some really dark areas there, and he had one of those really bright laser pointers and pointed out a bunch of stuff. But that's where I intend to bring a couple of my telescopes and have a look. Looks dark.
Yeah, that's not a bad place. If you Picket Post isn't much farther and it is darker, but if you don't want to go there, you can also go to a place we go to it doesn't have bathrooms, but it's the Weaver's Needle Vista Overlook. That's actually even darker than the park, and it's only 3 miles up the road. So that's another one to consider.
What is the Hyman Ranch, like the Star Party? What is that going to be on like the Bortle scale?
It's a Bortle 2, so it's nice and dark. There's going to be a lot of different equipment out there, so it's a really good experience to check out what other people have and everything.
You didn't mention anything about the smart telescopes like the C-Star or the Dwarf. Do you just consider those cheating, or?
Oh,
but
I've got a C-Star myself.
Okay, I do too. But here in the city, that you can do a lot of things that you couldn't do. So if you comment on
so
those.
the C-Star, okay, the reason why I didn't mention those is because those aren't really observational astronomy, and that's what I was more talking about. For the C-Star type of thing, C-Star has a wide field of view. Actually, and I've been thinking about that and looking recently. If you go to my guides, look at the size of the objects in those guides and look for larger objects. I was thinking dark nebula might be really good for C-Star, and the seasons right now is really good for it because the Milky Way's up. So if you check out the Sagittarius guide that I've got set up recently, it's like 60 pages that has some dark nebula in it and stuff. So that might be a good target. Also, the North American Nebula is up high in the sky right now. That's over in Cygnus. So yeah, you want some larger objects for the C-Star. In the city, the C-Star would be fine for like the sun and the moon. Planets, that's way too wide of a field of view. You can never do anything with that. Maybe open clusters in the city you could do, maybe. But city viewing is kind of limited. And if you are going to use a C-Star in the city, use the the filter, and you want to be focused on nebulas. But you can get nebulas in the city. So put it in your backyard, try the North American Nebula and some of the stuff like that, and you'll get some good results. Okay, thanks everybody.
Wait, we got Zoom.
James from online. What about narrowband filters for astrophotography in the city?
Okay, sorry, again, this wasn't focused on that, but that's a good valid question. I used to do a lot of astrophotography. Narrow bands in the city work really well. I mean, I would go in my backyard and I'll set up, the nice thing about it is I could set it up, let it run all night, every night, you know, for 10 nights and gather a lot of time. And the narrow bands are perfect for it. You can even do it when the moon is up. But yeah, I've had some, go to my website, you can see some of the pictures, the nebulas and stuff. Most of those were taken in my backyard. So narrowband in the city is a perfect match.
Thank you, James. You can just hang on to that. Before I introduce Mark, I want to share with you that he has written a new book. It is called The Solar Observer's Handbook, and it's got a lot of really good information in there. You received a ticket this evening if you were wearing your EVAC name tag. So somebody is going to win a copy of Mark's new book. And we will do that raffle when he's done with his presentation. But for now, I'm going to turn it over. Oh, no, I'm not. I'm going to introduce Mark. All right, so tonight we are delighted to welcome back a familiar face to EVAC. Our guest speaker is Mark Johnston, though many of you may also know him from social media, where he shares his incredible astrophotography and work as AZ Astro Guy. Mark has been leading public astronomy outreach across Arizona for over 30 years. He is a NASA Solar System Ambassador, Vice President of the Phoenix Astronomical Society, and serves on the Board of Directors for the Astronomical Society of the Pacific. Additionally, he is an ACEAP ambassador to Chile, a Telescope.live ambassador, and the author of the Solar Observer's Handbook. Having spoken at 2 of our monthly meetings last year, we are thrilled to have him back with us once again tonight. Please join me in giving a warm welcome to Mark Johnston.
That's very nice. Thank you very much. All right, well, tonight I'm going to be talking about the sun. I've been doing astrophotography for a long time, and like many of you, did M31 and M42 and all the crowd pleaser nebulas and galaxies and things and planets and the moon. But about 5 years, I got more and more interested, 5 years ago, more and more interested in solar. And it's really become my passion. And we're going to talk a lot about solar observing and solar imaging tonight. So a lot of people, when they see the sun, they think of it as the one object in the sky that never changes. It's just this bright ball in the sky. But actually, the sun changes more than any other object you can see with a telescope. And most of us as amateur astronomers spend our entire career chasing objects that don't appreciably change at all in your entire lifetime. So you're looking at a galaxy or a nebula or a star cluster. They're beautiful, they're amazing, but they're exactly the same as they were 30 years ago when you looked at it the first time. So the sun is very different. It can be different in 30 minutes. So here's an example of one of my time-lapse images. And you can see this is done with a hydrogen alpha telescope showing a plasma cloud draining back into the surface of the sun, along with a beautiful heteroprominence beside it. So this shows why, to me, solar observing is so addictive. The limb of the sun might be completely calm, nothing going on, and then this thing might arrive. And in fact, at the end of the presentation, I'll show you something that happened today that I captured this morning, and I just finished the time-lapse video at 5 p.m. this afternoon. So you'll be the first to see it. So prominences are often mixed up with flares. So people look at that and say, oh, look, there's a prominent, or there's a flare on the sun. Those aren't flares. So a flare is energy. We'll get into that a bit a few more minutes. A prominence is basically ionized hydrogen, which in technical terms is plasma. The sun's actually made of plasma. And this ionized hydrogen is suspended or moving along magnetic field lines, or can be pushed around by gravity as well. They look kind of sculptural, but as you can see from the time-lapse images that I take, they're not static. They do move quite a bit. And prominences come in many different types, which we'll explore later in the presentation. So this is a time-lapse of an active region. You can see a sunspot here in the center with the dark umbra. And then all around here, you can see fibrils. Fibrils is a solar term that refers to short-lived, elongated little strips of plasma that kind of wave in the magnetic fields around the active region. And they're all over the surface of the sun. And then you'll also see at the top, I'm not sure where we are in the time lapse, I wasn't paying attention. There are a couple of active filaments that show up. There's the solar flare happened just there. So that bright spot you see that appeared, that's a flare. So it's not this thing on the limb, it's actually energy. Flares are energy and prominences are matter. That's one way to look at them. So let me see. Okay, here's one. So if you look at the top of this image, you will see some filaments forming. These are these dark areas. There's one down here, one over there. And this is where the plasma rises off the surface of the sun, and as it does, it cools, and so it looks darker in a telescope. Now, this is the natural look on the left. On the right, I have done a static picture of a very large filament. It's called a quiescent filament, and it's reversed in luminosity in this picture. So this is what's called an inverted image. And I'll explain why I do inverted images a little later on in the presentation, but the short answer is they often show more detail than a natural image would show. And that you may think that sounds weird, but there's science behind it, which I'll get to in a little while. But this one, to put this in perspective, this might be 5 Earths across. Like, in fact, this pointer is probably a good representative size of the Earth. It's a little red disc, and maybe 30 or 40 Earths long. These things could be massive. They can be 100,000 miles long across the sun, and they can last for a very long time. So some of the things we see on the sun are very long lasting, like some of these quiescent filaments. They can last for weeks, and some things can happen just for 10 minutes and be gone again. Now, the sun looks different at different layers of its atmosphere. So on the right, you see an image of the solar photosphere. That's this area, this side over here. And you can see the center of the sunspot. You can see little light bridges and the penumbra is this outer part of the sunspot, then granulation around the outside. And when you first get into solar observing, the least expensive way to do that is with a simple broadband filter. I'll talk about filters in a little while. Filter that would go over the objective of the telescope, or you can use a Herschel wedge if you have a refractor and get this kind of a view relatively inexpensively for $200 or $300. You can be, if you already have a refractor like that one over there in the room, you can start doing solar observing safely. Now, if you want to look at hydrogen alpha, which is shown on the left, this is on the left side, we have what's called the chromosphere layer of the atmosphere that's above the photosphere. And that's where you see all the really interesting stuff like the coronal mass ejections and filaments and prominences and things like that that are really, really interesting. So you can also see in this left picture, just to kind of complete the discussion about prominences and flares, these long white strips here are called flares. You can get long strips of flares. You can get flare kernels, little spots. But the bright overexposed areas are basically where the energy is blasting out of the sun in a flare. It's not the prominence you see on the limb. Here's another couple of examples of white light images. The one on the right was actually a NASA APOD that I got in 2023. And then the one on the left is a full disk image you would get with a small refractor. And here you can see some of these light areas at the top. This is called faculae. That's area of high magnetic field, and hotter areas based on lighter. The dark spots are sunspots, as we talked about before. You can also see limb darkening at the edges of the sun, and you can also see transits. So I'm not sure how the sound's going to work on this one, but you can see, hopefully. Oh, it didn't work. Okay. Well, we saw that one. Let me go back up, see if I can do this again. All right. Okay, there's no sound here. So what I thought I had. No, I don't want to run sticky keys. Let me try this again. There's supposed to be an ISS transit going across the sun here. Let me try one more key press. Okay, I don't know why this is not running, but I think you saw the plane. There's the plane going by. And then here you can see in this picture, I'll point out with the red dot, that's the International Space Station crossing in front of the sun. I had a video of that on a cloudy day, but that's basically a high resolution of the ISS as it crossed the sun. And that's kind of one of the fun things you can do is try and capture an ISS transit with a solar telescope. This picture on the right is one that Buzz Aldrin put on his Facebook page. I'm pretty proud of that. Thought that was a pretty cool picture. And I think I have a video, a short time lapse. Yeah. So here you can see coronal rain following down. That's a very rare thing to see on the sun. And this is a static image of the same thing. So hydrogen alpha, where you see these really cool pictures, is at 656.28 nanometers and requires a very special filter on your telescope called an etalon. An etalon is something which notches out all the wavelengths of light except one really, really narrow strip at hydrogen alpha. And the main manufacturers of hydrogen alpha telescopes are Lunt Solar Systems here in Tucson, Skywatcher, who I'm sure most of you know, and Daystar. So if you look at this picture of the prominence, you can see Earth to scale. This is almost 100,000 miles high, this prominence, and obviously way bigger than our Earth. Now you can also look at other wavelengths at the sun. So I also look at the sun in calcium K, and calcium K is 393.4 nanometers. Now this is a wavelength which is really only good for most people as imaging. It's very difficult to see visually because it's way into the violet, way at the end of the spectrum. And so for most older people, as their eyes get older, it's harder for them to see well into the violet. So the young folks here might be able to see some detail. However, I'm at the age where I actually had cataract surgery, and then suddenly I can see everything in the calcium K. Okay. So in fact, I was down at Lunt Solar Systems with Andy Lunt. We're using his calcium K filter on a refractor. And he had a look and he said, I see a violet blur. And I looked and I saw that. Okay. So it depends on your eye, but most people use monochrome cameras and you add color later in post-processing. So the one thing about calcium K, which makes it unique, is calcium K is kind of the lower chromosphere and it shows magnetic field strength really carefully. So this light area here is called plage, and plage is from the French for beach. And it's the concentrations of high magnetic field energy. And this is the wavelength that shows that off the best. So if you want to know where the magnetic field strengths are on the solar surface, you can see that. Okay, I have another calcium K picture. Normally with calcium K, you don't get this level of detail on the limb. Here you can see a couple of spicules on the edge and a couple of small prominences. But normally you wouldn't see that level of detail. It depends on how narrow your bandpass is on your calcium K filter. I've got several of them. This one up here at the top right, you can see is calcium K. And then I took the same image at hydrogen alpha a few minutes later. So you can see that on the hydrogen alpha image, many of these fibrils and filaments are covering up what would be seen at the lower layer below it. So you can look at the sun's photosphere, you can look at calcium K, hydrogen alpha, you can look at helium D3. There's different wavelengths show you different amounts of information about the sun, which kind of makes it really interesting to learn about. Okay, so whenever you look at the sun, you need to look at it very safely. I've got a video where I had a picture of an eye, a piece of paper with an eye printed on it. And then I put my telescope with no filter on it. I point the eyepiece at the picture and right away it bursts into flames. And you don't want that. So I don't recommend that. So to look at the sun safely, most people use a all objective filter. So on the left side, you can see I've got a film filter here, a Bader planetarium film filter. You also can get solid glass filters. The film filters are much better optically than the glass ones are. And then, or another alternative, which is great for broadband imaging, is a Herschel wedge. So this diagonal you see here with a little Lunt symbol on it is actually designed to reject about 98% of the sun's light and then put the rest through a neutral density filter so it's safe to look at. And so I've got a camera on the end of the telescope here, and I'm taking broadband images in this example. Same with these two telescopes here. If you want to look at hydrogen alpha, then you can see on this diagram in the bottom, you've got the broadband light coming in. You go through an etalon, which rejects almost all the wavelengths except for a narrow wavelength at 656 nanometers. And then sometimes you go through a second etalon to make it even narrower notch. And then you go through a blocking filter, which gets rid of all the harmonics, and you're left with a single wavelength. That's what this telescope is doing here, the Skywatcher Heliostar, or here's a Lunt 60 millimeter telescope. Or you can also use different types of etalon. This is a solid etalon made by Daystar called a quark. This is a solar spectrum. This is sort of a Cadillac version of, this is the Chevy and that's the Cadillac as far as solid etalons are concerned. And then this is an example down at the bottom here of a Lunt calcium K filter. So all these different filters can be used to look at the sun at different wavelengths. But the important thing is to have the right filter and do it safely. Okay, we talked a little bit about that. Here's another couple of examples. These are some beautiful prominences on the left, on the limb of the sun. And then on the right-hand side, these bright areas, this little bright spot is a solar flare. The other thing that I hear on people say when they look at the sun is, look at the size of that flame on the sun. Well, there's zero flame on the sun. I hate to disappoint anybody, but there's no combustion happening. There's no burning happening. What's happening, I'll use an example most people are familiar with. If you have a stove in your kitchen and you turn the element on high, it starts glowing red, right? Okay. Is it on fire? No, it's not on fire. It's red hot. Okay. Well, the sun is actually much hotter than your stove. And so the hydrogen on the sun is so hot that it glows, it gives off light. And so what you're seeing is the incredibly hot ionized hydrogen, the plasma on the sun, it's glowing, and that's why you see the light that you see. Now, the true color of that is red. All my pictures are taken in monochrome, and you get a much higher quality image with monochrome than color, because if you have a color camera and you look at the sun, 3/4 of the pixels are useless because they don't see anything at all. You just want the red. So monochrome is better for that, and you add color in post-processing. But the flares are energy caused by magnetic field lines crossing each other. The sun actually rotates at different speeds depending upon the latitude. So it's about 28 days at the poles and 35 days at the equator. And so as a result, inside the sun, these magnetic field lines twist and touch, and when they reconnect, they give off gigatons of energy, and that causes some of these beautiful things that we see. Some of these structures are quite interesting. Here's a beautiful arc-shaped prominence. It's actually a filament because we're seeing it on the surface, but you can imagine in a 3D what that looked like. There's another one on the limb. And all these things are shaped by magnetism. So what you're really seeing is invisible magnetic fields and how they work on the sun. Now, in my book, I classify 17 different types of prominences. This is a loop arcade, and I'll see more about that later. This is a beautiful eruptive prominence here. There's a hedgerow prominence. There's a spray prominence. All different types of, there's an eruptive prominence here with detached plasma on the right. And you see every day things look different on the sun. It's pretty cool. Some prominences move very quickly and some move very slowly. A quiescent prominence, like the quiescent filament we talked about before, moves very slowly. So something like this might persist for several days. There's been a quiescent prominence on the sun that's been there for the last 3 days that's been imaged, and you see it on solar activity and other common social media quite frequently. Some of these are also very slow moving. This one here to me looked like kind of a monster stalking across the limb of the sun. Then you got active prominences. This is a spray prominence. It lifts off from the sun and scatters and dissipates. Sometimes you have surge prominences like this one will blast up and fall back down again. Another good example of a surge prominence here. These are some other eruptive prominences that blast way off and may actually detach and leave the sun and go off into space as a coronal mass ejection. Here's another video taken time lapse of a active prominence. So you can see individual little spikes of plasma are very short-lived and they fall back down into the sun. You can even see here on the surface what's going on right by the sunspot. So these active prominences are fascinating to watch. And while the still pictures are interesting, the time-lapse images really tell you, reveal what's happening with the physics and the magnetic fields. So, here, for example, you can see a magnetic field line would come over, arcing over, and would fall back into the sun. So quiescent filaments on the surface, there's the one we saw before. This one here, you've got the little spikes coming back down into the sun. Those are called magnetic foot points, and that anchors it to the sun's surface. I thought this one, to me, looked like a Klingon batla from Star Trek. Okay. This image is inverted. The sunspot is white. Normally it would be black, and the filament would be dark. In this case, it's light. I do that again to show more detail. I'll tell you about that in a minute. And then here on the surface, you can see some spicules. Spicules are little jets of plasma that lift off the surface of the sun, all over the sun. They're different from fibrils. Fibrils lay more or less flat along the surface, and spicules stick up vertically, but they're both plasma. Active filaments are much faster moving and short-lived and smaller than quiescent ones. So here's an inverted image showing several active filaments around some active regions. And then here's an example of in normal light, this is what they would look like. They're darker in the background. So active filaments are rooted near sunspots, and they often have plage, magnetic field regions nearby, typically smaller and shorter lived than quiescent. But they can be excellent targets for time-lapse work because they move so quickly. So as I said before, the sun is a magnetic object. It's by far the most magnetic object in the solar system. And there's a beautiful big eruptive prominence on the limb of the sun. And here is the photosphere version again. So this is broadband. This would be hydrogen alpha. So these spots you see are not just dark blemishes on the sun. This is where there is a large magnetic flux tube erupting vertically out of the sun. So wherever you see a black spot, there's an invisible magnetic field line erupting straight out of the sun and usually arcing over and going back into another sunspot nearby. And these are areas where the magnetic field strength is so strong that it suppresses convection, and so it makes it look darker and cooler. So the sunspot center is cool compared to the outside area, and then the part around it, the penumbra, is a bit hotter, and then around the outside is the hottest still. Again, these light areas you see here are called faculae on a photosphere view, and they're the hottest parts of the surface of the sun. So let's talk a bit about natural versus inverted image processing. For people who do solar imaging, this can be a controversial topic because a lot of people who look at it visually only don't like inverted images because they say it's not natural. It's not how the sun really looks. So on the left side, you have an inverted image, a natural image of the sun. And you can see on the limb, you've got an active region here, and you've got a prominence, and you've got some ejecta that blew off from the side of the prominence here. Now, I want you to look at the same picture in an inverted mode and ask yourself whether this area here is clearer in natural or inverted. Most people would agree that there's much more structure and detail visible on the right than on the left. These are identical images. I simply invert the luminosity to get the picture on the right. So why is that? Here's another example. So inversion does not add detail. All it does is remap the luminance. It inverts the luminance. Now, in doing research on this, I found out that the retina and the visual cortex do not process light on dark and dark on light the same way. They actually use different pathways into the brain. And there's a 2023 Journal of Neuroscience paper that suggests that luminance contrast the dominant shifts between on and off pathways, and that low contrast light targets can be located faster and more accurately than dark contrasts. So on the limb, basically what this means is inversion makes fine prominent structure easier to follow. So I'm not arguing that that's a true representation of what you would see in the eyepiece on the right, but I'm saying that often it reveals more detail than you would see with a natural luminance on the left. And this is not the only place it's done. So I've got a friend of mine who's a radiologist up in Scottsdale, and I asked him to send me a couple of x-rays. And so the x-ray on the left is a lung x-ray in natural view. And he told me that radiologists routinely invert the image because it's easier to find structures and things like medical problems. In the case of this image on the right, there's actually a catheter tip he was looking for. The green arrow shows where the catheter tip is. It's easier to see on the right image than it is on the left image. Another example would be the Solar Dynamic Observatory. So if you look at the right side, you've got 4 pictures of the sun. This is directly from NASA. And what NASA does is they assign different colors to different wavelengths of all their SDO images. And no one's saying the sun looks like that, but they're saying it's diagnostically helpful to look at it in different colors. Here's an example you're all familiar with. So here's the Pelican Nebula, IC 5070 in Cygnus. And on the left is how it looks with a color camera, because it's basically red, hydrogen is red. On the right, that's a narrowband image in the Hubble palette. So in the Hubble palette, what they do is they have a mono camera, and they have a hydrogen alpha filter, an oxygen 3 filter, sulfur 2 filter, and they assign different colors to different wavelengths. And when you do that, it's diagnostic because it tells you, this picture on the right, because you see the blue, you know it's primarily oxygen 3. And there's some sulfur in red and a little bit of hydrogen in green. So it tells you information about the nature of the gas making up the nebula. No one is saying that's how it really looks. What they're saying is diagnostically helpful to provide that level of information, but it's not real. So basically the message here is that both natural and inverted processing on the sun is okay, as long as you explain what you're doing. People find that you get more information sometimes in the inverted view, but and no one's saying that's how it looks naturally. But whenever you get things through a camera and start doing post-processing, it's never going to be exactly the same as the eye sees anyway. All right, so now I'm going to talk about some solar observing myths. So the first one I'm going to talk about is the best time to see the sun is when it's right overhead. So anybody who's done planetary imaging knows that when the Jupiter is at the zenith, straight overhead, you're looking through the least amount of atmosphere. And so therefore, you're going to typically have better seeing, and you're going to have the least turbulence because you're looking through the least amount of air. And that does make sense for planetary imaging, but the sun is different. In the morning, when the sun rises, it begins to heat up the ground. And it heats up rocks and pavement and building tops and everything. And as it does that, that heat starts to re-radiate back into the sky. And what that means is that the best time to see the sun is almost always between 1 and 3 hours after sunrise. You want to wait for at least an hour so it's high enough to get through the thickest part of the atmosphere. But if you wait too long till it's straight overhead, it's heated up the ground enough, there's a lot of turbulent air coming up, re-radiating off the ground. And so the best time to see the sun is typically 1 to 3 hours after sunrise, not when it's at the zenith. Second myth would be that a bigger telescope will always outperform a smaller telescope. With solar, that's not true. Okay, so making notes here. So with a larger telescope, you have more resolving power, theoretically, but the sun is not the faintest object, okay? This is not Stephan's quintet, okay? The sun is something which is very bright. So you don't really need a lot of aperture typically to look at the sun. And a wider aperture is going to have more turbulent air going through it. So if the seeing is not great, you'll get a better view with a 60 millimeter refractor than you will with a 120 millimeter refractor on the sun. And then the last comment here is reflectors are better than refractors. Well, it's true that reflectors provide more resolving power, more aperture per dollar, and that can be very important at night if you got a Dobsonian or a Schmidt-Cassegrain. But again, with the sun's a bright target, and refractors typically work better than reflectors. First of all, with a reflector, you almost always have to have a full aperture filter, and it makes it very hard to do hydrogen alpha imaging. You're really relegated to broadband only with a reflector. Whereas with a refractor, you can take your own refractor and add a solar spectrum or a Daystar Etalon to the tail end of it where the focuser, just after the focuser is, and see H alpha. Or you can get a dedicated H alpha scope like a Skywatcher or a Lunt. But refractors generally are better than reflectors for solar. A narrow H alpha filter is better than a wider one. Well, when you double stack a hydrogen alpha telescope, you end up with a narrower bandpass. That does several things. The first thing it does, which is great, it gives you much more contrast on the surface of the sun. But that comes at a cost. First of all, you have about a 20% dimmer image because you're narrowing how much light can get through here. So you're not seeing as much data. Also, the sweet spot gets smaller where you've got the best uniformity of the image. So you'll get a better uniform image with a single stack with a brighter image than you will with double stack. But double stack does give you, if it's tuned properly, a really good image with much more contrast on the surface itself. Solar observing is financially out of reach for most amateurs. Well, that's not true. You can take a standard refractor, which many of you may already have, or a reflector, and get a broadband filter to go over the objective, or get a Herschel wedge from someone like Lunt or Beta Planetarium, and take some amazing broadband images of sunspots and solar transits and things like that. And you can get a hydrogen alpha telescope like a Coronado PSK on the used market for about $300 and do H alpha viewing, and then go from there. Next two here. So if you've mastered DSO imaging, solar processing is easy. Well, it's completely different. So now there are some things that are similar. Understanding how cameras work and histograms, how to focus a telescope, those are fungible skills. But there's no 10-minute exposures with the sun. You're trying to capture very short, fleeting, high-speed videos where seeing is extremely important, and understanding the length of time that you hold the shutter open and what you're looking at makes a big difference. And then last, solar max is the only interesting time to view the sun. So the sun goes through an 11-year cycle where it's very active, which it was in 2024, and then it gets less and less active, and then it gets more and more active, and doing that for 300 years, and they started measuring it. And some people think, well, solar minimum, nothing to see. Well, that top right image was taken by an amateur in 2019, which was the bottom part of solar minimum. We're 2 years away from solar max. On Wednesday, I took these 3 pictures. So those 3 pictures at the bottom are ones I took from my backyard in Scottsdale 2 days ago, and we're 2 years past solar max. So there's still lots of stuff to see on the sun, no matter what time you look at it. Now, this is a bit of an eye chart. I don't expect you to be able to read that necessarily in the back, but suffice to say, I've put in my book some information that tells you kind of what sorts of features you can see on the sun based on what aperture you've got in your telescope. So the wider the aperture, the more resolution you get and the more detail you can see. I also put some details there on whether it's hydrogen alpha or calcium K. So temporal aspects, I mentioned this a little bit before. If you look at this prominence on the left, this is a quiescent prominence, and that stayed stable for over a day. And it's beautiful to watch the plasma rising and falling on the edge, but it lasts a very, very long time. The one on the right lasted about 5 minutes and was gone. I do a repeat. I show it twice here, but that surge prominence, the jet prominence on the right, which just it jumped out of the sun and fell back down again, and it was gone again. So some things are really quick, some things are really slow. Some surface features like sunspots can last for a very long time, and there's a lot you get to learn when you're looking at the sun as to what types of setups you should use to capture what types of beautiful pictures. Then there are some structures that are really interesting. The top left is a horn prominence, and I've only seen one once in all the years I've looked at the sun, and I look at the sun almost every single day that it's clear. This is a coronal mass ejection in the middle. This is a beautiful surge prominence seen almost in a 3D view on the surface. Over here, you've got a very rare prominence in the lower left, which is a tornado prominence, where the plasma comes up and twists around itself. I wish I got a time lapse of that, but I couldn't. And then there's a beautiful spray prominence. So all these ones have unique different shapes. And this, for me, what makes it so much fun looking at the sun every day is you always see something new. It's a new view, new prominences, new sunspots, new filaments. There's always something happening that makes it different every time you look at it. So the sun is never the same twice. Here's a beautiful picture of some suspended plasma draining back into the coronosphere. Every day offers a new view. So unlike looking at galaxies or nebulas, the sun's going to be unique every single time you see it. And if you are interested in solar observing, you don't need to get the biggest telescope on day one. I mean, the best telescope, and this is true for nighttime as well, is the one that you're going to use. So one that's easy to set up, easy to take out. And one thing that's cool about the sun is you can go to certain websites like the Solar Dynamic Observatory website from NASA, and they take pictures of the sun from space every 10 minutes and download them back to the Earth. So you go to the SDO website, I've got the app on my phone. The first thing I do when I get up in the morning is pull up the app and see what's happening right now on the sun. And this morning I jumped out of bed. I'll tell you why in a minute. So let's move on from here. So a bit of a summary here. So now you know sunspots are magnetic storms. Prominences are matter, suspended plasma. Filaments are prominences seen against the disk. Flares are magnetic energy released in short periods of time. And the sun is a star you can all watch in real time. So you've seen different structures and you know a lot about magnetism. All right, so now I'm going to switch tracks and talk about the astronomical reason barns are red. All right, so traditionally barns have always been painted red. Now, why is that? They were painted red because there's a lot of surface area to paint and they want the cheapest paint possible. And in the old days, red was always the cheapest paint. Okay, so why was red the cheapest paint? The cheapest paint because the red pigment was the most abundant natural pigment found on Earth. Now, why is that? Well, the pigment comes from something called ferric oxide or hematite. It's Fe2O3. So iron and oxygen are two of the most common elements in the surface of the Earth. And they're found in all types of rocks and very, very common minerals on the surface of the Earth. In fact, it's found on Mars. The Mars rovers find hematite all over the surface of Mars, which is why it's the red planet. It's why you've got red blood. The oxygen is red. Okay, so how did all that iron get in the surface of the Earth? Well, when the Earth was formed 4.5 billion years ago from a big cloud of gas in space, that cloud of gas was rich in iron. And so when those elements fell together to form our planet, a lot of the high probability of the high amount of a certain atom was iron. A lot of iron was there. So you might say, okay, well, how did that iron get into that cloud of gas? Well, a few billion years before that, there was a very massive star reaching the end of its life, and it fused hydrogen to helium and helium to other elements all the way down to element 26, which is iron. And there's a big ball of iron in the core of this giant star. And at that point in the nuclear physics, the fusion in a giant star stops. And then suddenly, gravity, which has been fighting against the outward pressure of fusion for millions of years, says, I win, and the whole star just implodes on itself and then explodes in the biggest explosion in the universe called a supernova. And then all of the material that was in that star is blasted out into space and spread for light years in all directions in a gigantic cloud like the Orion Nebula. And then millions of years later, or even billions of years later, part of that gas cloud gets upset by some passing star or something, begins to contract, collapse upon itself. You get a protoplanetary disk, and you end up with a star and planets like our Earth. So the short answer is barns are red because of how massive stars die. It's true. All right, so the sun's stable now, but it's not going to stay that way forever. So we are about 5 billion years old, 4.5 billion years old in our star, about halfway through its life. So about 5 billion years from now, the sun will build up a very large core of helium, and then it will get hotter and hotter, and the sun will begin to expand. It'll become a red giant. It will engulf and destroy Mercury. It will engulf and destroy Venus. It'll come right up to about the edge of Earth's orbit. And so astronomers are undecided. There's some debate about whether it will be vaporized or just burnt to a crisp. But either way, it won't be a good time to be here. about 5 billion years from now. And then shortly after that, that outer shell of the star will puff off in a big cloud of gas, which we call a planetary nebula. So it's going to look like the ring nebula or the dumbbell or the helix that we all see in our backyard telescopes. And then eventually that gas will expand away and we'll be left with a white dwarf, which will slowly cool over billions of years. So on the time scale of our lifetime, there's all kinds of cool stuff happening on the sun, but the sun is not permanent either. So meanwhile, this morning, one of the rarest things on the sun is a loop arcade prominence. This is a loop prominence that has many, many arms. And not only do you see the loop, this is from this morning, I caught this today, but there's this also plasma rising behind it. Now it doesn't actually go through there, it's actually behind. You can tell because it's not being pulled up through the magnetic field channels in the loop prominence. But this is almost a 3-hour long time lapse that I took from home this morning. I saw this on the edge of the sun when I pulled up the SDO image on my phone, and I went, yikes, and I ran outside. And as soon as the sun got high enough, I started taking a video of it. But that's, to me, what's so cool about the sun is you get to see things like that once in a while. All right, so most of the content here is from my book, my Solar Observer's Handbook. If you want to take a picture of the one on the right, I've got a PDF version, which you can save 20% off with Solar 20 if you want that. And then the Amazon soft cover is the one that's going to be raffled off momentarily. And I also have a few more I brought in a box. If you want to buy one from me, I can sign it. If you want, I can do that too. So anyway, the main thing I want to take away is that the sun is a really cool object. Not so cool, hot, but it's really interesting and it's dynamic and it changes all the time and it's affected by magnetic fields. And anyway, I hope you learned something about the sun today and thanks very much for having me.
All right.
I'll take a few questions.
Oh, we'll start right here.
Yeah, two quick questions. What is about the focal length that most of those videos are shot at? And second question is, do you use a standard mount like a AM3 or AM5 or something specialized?
Most of the full disk images are taken at f7 with like a Lunt 100 telescope. Most of the high resolution close-ups like that are taken at f28, about 4.4 meter focal length. So basically it's a f7 telescope with a 4x power mate and then a camera on top of that. As far as mounts go, I have most of my work is done with either an AM5 or an AM7. And I also have an Altaz mount and some other stuff, but most of it's AM5, AM7.
More questions. Okay.
Two questions for you. The first is, what's the most cost-effective way to get into hydrogen alpha viewing?
So I'd ask you a question first, and that would be, do you have an existing refractor?
No, I have a Spitcast Grand with the foil filter.
Okay, so if you want H alpha, you really can't. I've got a C925, which is great. I use it for EAA, hyperstar presentations for the Four Seasons and things like that, but it's no good for the sun. So for the sun, you really should get a small refractor. You don't need, now the nice thing about H alpha, it's only one wavelength. You don't need an apochromat. You can do, an achromat's fine. So you can get like on cloudy nights, an inexpensive 80 millimeter refractor, for example, or any aperture, but 80 is a good number, 80 or 100. And you can get a quark chromosphere, like that. I showed one of them on the image, and stick that past the focuser, and that'll give you like a 0.7, 0.6, 0.7 hydrogen alpha view. You can also get on cloudy nights a lot of used telescopes that are quite good. You get like a Lunt 60, or you get, I'm not sure how many Heliostars are on the market yet because it's a fairly new telescope, but a used Heliostar 76 would be a good telescope. So either you take an existing refractor and add an Etalon to it, or you can buy a dedicated H alpha telescope used on cloudy nights or Astromart. Yeah, so the sun is actually heating up slowly all the time. As the helium core gets larger and hotter, it causes heat. So the data that I've seen suggests in about 1 billion years from now, the radiation from the sun will be enough that our oceans will have evaporated. So you got about 1 billion years to go. Well, I've got, let me look at my phone here. What you want to do is find the Solar Dynamic Observatory. So it's, let's see, oh, it's the wrong one. Called Solar Monitor. It's free. It looks like a big red square with white circles in it, called Solar Monitor.
Awesome, thanks. My other question is, I guess I could go look this up, but you mentioned it, so I want to ask you because maybe you know. You were talking about the supernova that happened before our solar system was here, that created our solar system. Have we named that star? Does that have a name?
That's the supernova that preceded our, no, it's
No?
not there anymore.
Yeah, but I mean, it feels like it should have a name. That's all.
Will the sun will it have a supernova, or will it just like slowly expand, like release its gases?
What will happen with the sun, you're saying?
Yeah, with the sun.
So as I mentioned, in about 4.5, 5 billion years, the helium core will get hotter and hotter and larger, and that will cause the sun's outer atmosphere to expand, and the sun will become a red giant star, and it will become about as big as Earth's orbit, so way bigger than it is now, which will make obviously life impossible here. So hopefully Elon Musk will have us living on, Europa or something by then.
One up here in the front.
All of the things that you've seen through your observing, what's been your favorite?
Favorite solar thing I've seen? What's really satisfying is to catch an ISS transit. I've got a video on my YouTube channel on how to do this, but there's a website that tells you when the ISS is going to go overhead where you live next time. And you can look at that, and then you have to plan to be in that exact part of the city or outside the city, wherever it is, at the exact moment. It takes about 0.4 of a second for the ISS to go across the sun. So you have to start capturing video before it comes across. And so it's a fair bit of work, but if you get everything focused and you're at the right place at the right time, you get a really great picture. To me, that's kind of really satisfying.
Were you able to see anything during the solar eclipse last week?
Yeah, I was here for the solar, was I here? I was here for the solar eclipse. I was in Canada recently, but to me, 99% coverage is a waste of time. You need totality, okay? So I've seen several solar eclipses, and I'll be at the one in Luxor. By the way, whatever you have planned for next August 2nd, cancel it and be in North Africa or Spain, because the longest total solar eclipse in 100 years happens next August 2nd. We'll have 6.5 minutes of totality, which is incredibly long. And in Luxor, Egypt, and I'll be with a group, I'll be the solar expert on a group over there for that event. So I wasn't doing anything with the sun for the recent eclipse. It was only partial here. It just makes the sky a bit dimmer. But when you see a totality like what they had in 2024 here, and also the one that was in Texas and the one that was in Wyoming, and I've seen them elsewhere, they're breathtaking to see where the moon completely covers the sun. You see the corona. You never see the corona unless it's 100% covered.
All right, more questions?
Yeah, you mentioned there's mass ejections from the sun. What kind of particles are they, and what velocity are they at?
So it can vary. So basically it's hydrogen. It's so basically all the stuff you're seeing is ionized hydrogen, so protons and electrons. And there can be gigatons of matter leaving the sun. I mean, every single second in the sun, it converts about 4 billion tons of hydrogen into energy using E equals mc squared. Plus you lose about another 2 billion tons in solar wind radiating particles away from the sun in all directions. So even at that, the sun's been burning for 4.5 billion years, and it's losing billions of tons of matter every second, but only what I've read is 0.013% of the sun has gone due to that over the last 4.5 billion years, because it's so big.
So in all the pictures, we always see the sunspots as these little black spots, and we always talk about what's going on around it and or out of it. Are you able to get any saturation? Overcome the contrast and actually get definition in the sunspot to see?
I mean, in the umbra itself,
Within the sunspot.
in the dark pot, the
Yeah.
dark center part, yes, not easily. So it's basically if the rest of the sun wasn't there, the central black part of the sunspot would be brighter than the full moon. Okay, but because the rest of the sun is so much brighter, it looks dark relatively. Okay, sometimes within the umbra you can see some small structures, but it's very difficult. You have to have excellent seeing. I mean, the gentleman asked earlier about how to get good seeing. There's an app which is excellent called Medio Blue, and Medio Blue, the website's actually better than the app, but the Medio Blue website will tell you by the hour what the seeing is at any GPS coordinate you want, as well as the jet stream amount and how much cloud cover there is, both low, medium, and high. And I look at that every day. One of the best places for looking at the sun near here is the summit of Humboldt Mountain. So Humboldt Mountain is that one you see with the big white dome on it, north of Cave Creek. It's about an hour from Scottsdale, and it's 5,100 feet. So it's high elevation, which gets you above a lot of the thick air. And there's typically 0.5 arc second seeing there, sometimes down to 0.4. To get better than that, you've got to go higher elevation and further from the city. So one of my favorite places is Willow Springs Lake up north of Payson. That's about a 2-hour drive for me. And I can get down to about 0.3 arc seconds of seeing on good days. And because you're looking across the lake, when you look across water, that laminar airflow makes the seeing really steady. So you want to be getting away from rocks and buildings and pavement and things like that.
So I have 2 questions. So what isotope of hydrogen is in like the sun's atmospheres and stuff?
So
is it protium, deuterium, or tritium?
So I'm not even sure I know the answer to that. Okay. I know that all of those are there. And if you look at the proton-proton chain, when people say in simple terms, 2 hydrogen atoms squished together to make a helium atom, it's actually way more complicated than that. And I describe that in my book. But so there is deuterium in part of that proton-proton chain to create a helium atom, excuse me. But as far as the majority of the surface of the sun, it's just ionized hydrogen, which means just protons and electrons. You only end up with deuterium and tritium and things where you have 2 and 3 bonded together, neutrons bonded together, when you have higher pressures and temperatures. And on the surface, you don't have the higher pressures that you'd have inside the sun. Most of the nuclear physics stuff happens inside where it's much more dense.
Okay, so on my second question, where's a good nearby place to get hydrogen alpha filters?
Where's a good place to get them?
Nearby, or at least it's somewhere in the state.
Well, if you can buy them online, of course, from anywhere.
Yeah, I know.
But if you want to physically go to a place, one of the largest manufacturers of hydrogen alpha solar telescopes in the world is right here in Arizona, Lunt Solar Systems at 2525 Coyote Drive in Tucson, Arizona. So in Tucson, Lunt makes these things. I don't believe there's any other manufacturers. There's probably the best astronomy store in the state is Starizona, also in Tucson. And they sell a Skywatcher heliostar telescopes. They sell Daystar quarks. They sell Lunt Solar System telescopes. Lots of different hydrogen alpha telescopes are sold by Starizona. You can actually go to their store when they open, and they'll take a telescope out in the parking lot. You can look through it and see what the H alpha sun looks like that day. But the manufacturers would just be Lunt here in the state, and then probably to actually get your hands on something. There really isn't, and maybe someone can correct me, I'm not aware of any really great store in the Phoenix area for astronomy. You really have to go to Starizona, I think, to get that kind of gear.
More questions?
I'm not sure if I'm using the right term, but have you seen those tunable spectrographs, I think was what they are, that they use for?
Spectroheliographs?
Yeah.
Yeah, I've got one.
Okay.
So the ML Astro one is the one that's easiest to use, but they're still way harder to use than a regular telescope because you have 3 different focuses. You've got to focus the slit and the collimator and the camera all independently, and they affect each other. So it's an iterative process, but you get some amazing pictures in H alpha and calcium K. So what he's talking about here is a device that's kind of a V-shaped device. It's called a spectroheliograph, and you attach it to a refractor and you put a camera on. It's not a visual device, it's imaging only. And it does a scan across the slit, and it ends up with a very high resolution, high contrast picture of the sun. Now, because it's a different mechanism than we use for the traditional lucky imaging that I've talked about this evening. And so as a result, you can get higher contrast, but you get lower resolution. So because each slit can have different seeing, you can see vertical lines through your image if you don't have good luck with seeing during the scan. But they can produce some amazing pictures. I've got a video on my YouTube channel where I review how they work and also talk about them in the book.
Yes.
But yeah, spectroheliographs are great, but they're hard to use, and it's an imaging only discipline.
Yeah, it seems like the interesting thing about that is you can tune it to the hydrogen alpha or the calcium or all these other wavelengths.
Yeah, hydrogen. You can look at helium D3, all kinds of wavelengths.
Thank you.
Yeah.
All right. Any more questions? Oh, John, you got some on Zoom? Okay.
Not specifically about our sun, but Tricia would like to know if stars appear in all colors of the rainbow, and would the surface of a black hole appear like our sun if it was visible?
So first question is, stars are not all colors of the rainbow. So you never see a green star, for example. Most of the other colors you'll see. You see orange and blue and red and violet, and white. But like our sun broadcasts most strongly in the green wavelength, but because it's a broadband spectrum, we see white to our eye if you're in the space station. Sun looks yellow on the surface of the Earth if you're looking through the atmosphere because of the Rayleigh scattering in the atmosphere. But if you're on the ISS space station and you're looking at the sun from up there, it's white. So that's the first question. And the second question was about black holes. Okay, would the surface of a black hole appear like the sun? If it was, well, this is not my specialty, but the best answer I can give is a black hole by definition is the absence of light. Now, you do see as things fall into the black hole and hit the accretion disk, they get torn apart by tidal forces and they radiate a lot of energy before they fall in. So when you look at a black hole from a distance, you can, if it's an active galactic nucleus, for example, like a quasar, it's ironically the brightest thing in the universe, even though it's supposed to be the absence of light. But for like we're talking about a stellar black hole, then I don't believe you would see anything on the surface because it's not radiating light. Light can't escape.
We have another question up front. Any more Zoom questions, John? Okay.
This is fascinating. I wonder what is the purpose of observing? Purpose. I understand that this is like you learn more about sun, and then kind of safety is another thing. Like if there are solar winds and other things, is there any other purpose?
Sure. What is the purpose of observing the sun? Well, for me, it's educational, but the sun affects the Earth tremendously, right? So it can affect satellite communications. There's a very famous event back in 1859 called the Carrington event. You can look it up on Google. And there was a coronal mass ejection from the sun pointed directly at the Earth. And when it hit the Earth, now back then, the only technology we had was teletypes. The guys who go click, 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 click to send a message down the railroad track. Well, those guys who were doing they got electrocuted because of all the current induced on the wires from the coronal mass ejection, and sparks flew out and they burst into flames and things like that. So if that type of event happened today, it would basically knock down the entire power grid on the side of the Earth facing the sun and destroy all the satellites and kill any astronauts in the space station. So knowing that's going to happen is helpful. Okay, so there has not been a Carrington class event since then. So the solar flares are classified in M class and X class. And the brightest ones that we see are X class, and they're logarithmic. So an X2 is 10 times worse than an X1. And it was estimated that the Carrington was an X45. And the brightest one we've seen since we started measuring them is about X6. Okay, so it's way brighter than anything we've seen in the past. But the sun affects, we had people on the Zoom who are in the ham radio group in Mexico, and they know the sun affects their ability to transmit radio signals. Okay, so the sun affects our ability to maintain our high-tech lifestyle. Okay, and it obviously affects weather and things like that too. So understanding how the sun works and what may happen to it as it evolves affects us tremendously.
And another Zoom question, Mark, if you want to share your mic.
Is it true that our sun is going through unexpected or unexplained gyrations currently?
I'm not aware of the sun going through. Now, on a macro perspective, the sun goes through a cycle, the 11-year cycle. We talked about that. 5 days ago, the surface of the sun was fairly quiet. There was like 1 or 2 very small sunspots, a couple of very tiny prominences. And then 3 days ago, it erupted with all kinds of cool stuff. And then this morning, there was a gigantic loop arcade, which I showed you earlier. So day to day, there can be a lot of variation, but there's nothing that I'm aware of that's unusual happening on the sun right now.
All right, any other questions? Okay, let's raffle off that book. Andrew, do you have the tickets? Thank you. So let's all give Mark a big thank you. Thank you. Incredible book. Okay. All right, so 082355. Wonderful, congratulations.
Congratulations.
So happy for you, Margaret. Yes. And Mark will sign that for you. All right, thank you so much for attending, everyone.